Hey everyone, and welcome. Today we're going to unlock the fundamental rulebook that engineers use to build our world. From massive bridges to towering skyscrapers, it's a set of ideas so powerful they literally keep our world from falling down.
So let's just dive right in. Have you ever looked at some giant structure and wondered, how do we know for sure that it's going to stay up? It's not magic, right? Well, the answer lies in a field of study that translates the language of physics into the art of building things. And that field is called engineering mechanics. The best way to think about it is like this. It's the foundational grammar for understanding how every single structure around you interacts with the forces of nature.
At its heart, mechanics is actually pretty simple. It's just the study of what happens when you push or pull on something. Does it move? Does it bend? Does it maybe even break under the stress? Mechanics is the science that gives us all those answers. So this whole world of mechanics kind of splits into two big areas. You've got the study of fluids, like water and air, and the study of solids. To understand how things stay up, we're going to park ourselves squarely in the mechanics of solids.
And this is where we find what I like to call the engineer's most powerful secret. It's almost a cheat code that makes pretty much all of modern structural design possible. And it all starts by facing a very messy reality.
Just think about it for a second. Is there anything in the real world that when you push on it, stays perfectly still and doesn't bend at all? The answer, of course, is no. In reality, every single object deforms, even if it's just a tiny microscopic amount. And that creates a huge problem for doing the math.
And this slide right here shows the engineer's brilliant solution. On one side, you have reality. It's messy, everything bends and squishes, and calculating that is incredibly complicated. But on the other side, we have an idealization, the rigid body. It's a powerful simplification where we just pretend an object doesn't deform at all. So here's the crucial point. By assuming objects are perfectly rigid, engineers can figure out all the big picture external effects, like will a building move, or what forces are its foundations feeling, with amazing accuracy and with way simpler math. This assumption is called the rigid body idealization, and it is the absolute bedrock of everything we're talking about today.
Okay, so with that huge assumption, our rigid body, locked in place, we can start to really analyze the most fundamental concept of all, force. We don't need some complicated textbook definition here. The best way to think of a force is simply as an interaction. When two things touch, they interact. That interaction, whether it's a push or a pull, is what we call a force. Simple as that.
And to really understand any force, you've got to know three things about it. First, its magnitude. How strong is it? Second, its direction. Which way is it pointing? And third, its point of application. Where exactly on the object is it being applied?
All right, now this is cool. Because we made that rigid body assumption, we get this awesome engineering superpower. It's called the principle of transmissibility. It basically says that for a rigid body, you can slide a force anywhere along its path, what engineers call its line of action, and the external effect on the body stays exactly the same.
And this illustrates it perfectly. Check out case one. We have two forces pushing inward, compressing the box. On the outside, nothing happens. The box doesn't move. Now look at case two. We just slide those same forces along their line so they're pulling outward. Now the box is in tension, but what's the external effect? It still doesn't move. As far as the outside world is concerned, these two situations are identical.
But forces don't just push things in a straight line. That's not the whole story. They also have this other effect, a tendency to make things spin or rotate. And of course, we have a special name for that.
That twisting effect is called a moment. It's basically the rotational power of a force. And what's fascinating is that it depends on two things equally: how strong the force is and how far away it is from the point of rotation. A small force a long way away can create the exact same twisting moment as a huge force right up close. Okay, so let's take this a step further. What if you wanted just the spin? No push, no pull, just pure rotation. Well, for that, you need something very specific called a couple.
So here's the key difference. A single force, if it's not right on the center, will try to do two things at once: move the object, which we call translation, and spin it. But a couple, that's a pair of equal, opposite, and parallel forces, perfectly cancels out that push-pull effect. What are you left with? Pure, unadulterated rotation. No movement, just spin.
And you've done this thousands of times without even thinking about it. When you turn a steering wheel, your hands apply two equal and opposite forces. You're not pushing the wheel away or pulling it closer. You are applying a pure couple to make it turn. It's a perfect real-world example.
All right, we've got forces that push, and we've got moments or couples that twist. Now let's put it all together with a master technique engineers use to move a force from one place to another.
So how do you actually move a force without changing the physics of the situation? It's not as simple as just picking it up. Engineers use this really clever trick. First, at point B, where we want the force to be, they add two equal and opposite forces. Since those just cancel each other out, we haven't really changed anything, right? But now, check this out. The original force back at A and the new opposite force at B, they form a perfect couple, a pure twist. So what are we left with? Well, we have the force we wanted, now acting at point B, plus this brand new rotational effect. And that's the crucial takeaway. Moving a force creates a moment.
So, what's the big picture here? What's the main thing to remember? It's that this entire stable, predictable world that engineers design is built on one clever simplification: that rigid body, which then unlocks a few simple, powerful rules for managing all the pushes, pulls, and twists. And hopefully, this changes how you see the world just a little bit. The next time you look at a massive crane or drive over a long bridge, you'll know the secret. You'll see what the engineer sees, not a messy, bending, complex reality, but an elegant system of rigid bodies, where every single force and every single moment is perfectly, beautifully in balance.